Good morning, good evening, good afternoon. Good morning, good evening, good afternoon. Today I am going to go through a demo of how to use Levyx Xenon for a financial risk analytics use case. The specific use case I'll be showing you is backtesting an algorithmic trading model that uses stock options. So this particular model consumes a lot of data and at the same time requires a fair amount of compute. So the basic testing we're going to be doing on this trading model is reading in 1 year of stock market data and running several scenarios of potential parameter settings for the trading model through 1 year of trading data, and then simulating and comparing the results and deciding which parameter settings for the model would we expect to make the most profit and loss over the year. Specifically, what we'll be doing in this demo I'm about to show is we will first ingest the stock market data into a Spark Levyx data frame. We then will pre-calculate all the stock option values that we would need to use, about 7.5 billion of them, store them in a data frame, then use all that data, stock market data we've ingested, the pre-calculated numbers to calculate 50 different scenarios for 40 symbols or 40 stocks, running them through as if we had traded them for a year with those parameter settings, and then calculating the P&L, the profit and loss from each of those settings. So I jump into my notebook, I hit run. The first thing that's happening, and this is accelerated over normal speed, is I'm showing you the performance of running this entire backtesting run for 40 symbols, 50 scenarios, computing 7.5 billion option calculations. Specifically, I'm focusing in this slide on what is known as the stage 2 time. That was that time to pre-calculate the option values. So by using a hardware accelerator, in this case an Intel FPGA, I was able to accelerate the time of that stage 2 by a little over 3.5 times. So I was able to do stage 2 in 450 seconds instead of 1380 seconds. Now, I am pretending to be an analyst, a stock market quant running these things. So that would have run. Next, I would go in here into my Jupyter Notebook, which is a popular research tool for end users. You can see that I've documented everything I'm doing. Those are the commands that I just ran that you saw the results of in the previous graph. Now I want to look around in the resulting data tables that come out of that. So what do? I connect to Spark. Yes, I'm going to look at these various data tables that have all been stored in Xenon, in this case on SSD. The first thing I'll do is I'll actually look at the performance runs if I was coming in here and see how long it took. Does that seem to be the appropriate amount of time, and so forth. Next, I'll just look at a sample symbol. So in this case, I'll look at the stock HACF. I'll show the first 1,000 rows of the stock market data that I took in. It's showing bid prices, ask prices, volatilities. This is all the various tick data that was I originally ingested for the year. Next, I'll look at my options table. That was that pre-calculated table that I calculated. So it's showing me various spot prices and option strike prices. As you can see here, I did a query to look at the data frame, and it shows me that there were 3.7 billion synthetic stocks calculated, each synthetic stock being made up of two option prices, a call and a put. So I calculated a little bit over 7.4 options. That number seems right to me. The next thing I'm going to do is do some ad hoc querying into these data frames by using SQL. So I register as an SQL table the options data frame. First thing I want to know is, did I actually run on 40 stocks? So I just do a select distinct from that options table, and the output is indeed 40 stocks. The next thing I'm wondering is, how many distinct underlying stock prices did I have to calculate it on? By doing a count, I get 45,000. That sounds sensible. If I had 40 stocks, a little over 1,000 different price points per stock. Now I'm going to do a random selection from the options table. So I'm just looking for things where the option price was between 50 and 60, showing the first 1,000 rows of that table. And you can see that I can see the output there. You'll note here that that table was created, that query I just ran had 6.9 million rows coming back. This is why I need a platform like Jupyter or Xenon to run these things on, because these size tables are not really tractable in something like Excel or typical analytics tools. So I need some big data tools. Now, let me just show you why we built this demo in the first place and how we got there. So for these use cases, Apache Spark is a popular framework. It's open source. It's well supported in the industry. It's low latency, so it runs fast. It has an in-memory data flow model, which also makes it fast. I mean, fundamentally, what we were doing is taking that in those jobs that I ran, we were taking the problem I described, handing it over to Apache Spark and letting Apache Spark break the tasks up. Each of those 40 symbols were run on multiple cores, and then the answer is consolidated. So Apache Spark is popular, but it suffers from some I/O bottlenecks. As you recall, I talked about how many terabytes of historical data I was putting into Spark. By default, what Spark is going to do is it's going to load all the data that it needs to use up into a data frame that is resident in RAM. And that's fast, but can be a problem if you don't have enough RAM. Or alternatively, it can be costly because you have to scale your Spark cluster out to have enough RAM to accommodate the size of your data. So these I/O bottlenecks is what Levyx initially started working on. And that's why we came up, one of the reasons we came up with Xenon. So what Xenon is it's Levyx's clustered product. It's resident on top of SSD, storage class memory, all flash arrays, and RAM devices as well. It creates a live persistent data set abstraction across the cluster. So basically you can think of a giant table that you have low latency access to that's persisted across a cluster but available as if it's in RAM. We provide indexed operations, efficient scan support, and I'll get into a little of these cool query offload capabilities. The other thing we do that I just showed you in that demo is we have the ability to use user-defined functions to call things like FPGAs and GPUs. So in the demo I just showed you, the Black-Scholes calculations were actually running on an accelerated module on an FPGA. The reason Xenon is well, let me go through a couple more results and I'll explain. So when we originally came across this backtesting use case, we ended up doing several public benchmarks. This is one of them that we did with Vixata, an all-flash array vendor. This was for just regular backtesting of stock market models. So there were no options involved in these models. So no additional big compute required. But we were able to show that we were able to break through this I/O bottleneck that Spark had and show linear performance as you increase the number of, in this case we were doing 960 stocks at the same time with 300 simulations each time, and getting good linear performance as we added resources to the cluster. That results in significant economic benefits. So we did some tests running on standard Amazon nodes and then ran on Xenon on those same Amazon nodes, and we were able to show that we could reduce the cost because we needed fewer nodes basically by to do the same amount of work in the same amount of time by as you can see, a little more than 40%. Then we started looking at these calculation problems, these risk analytics runs where you needed to do complex math as well as just read and write a lot of many terabytes of data and compute across it. And the challenge we are solving with Xenon is, without something like Xenon and without some of these compute accelerators, you are stuck just expanding the number of servers you have to run on, and that can be really expensive. What we're proposing instead is using Xenon to have fewer servers densely populated with accelerator cards in them. These can be GPUs, they can be FPGAs, they can be, we're working with a company that has cards that have multi-core processors, 256 cores on a card. The challenge of using the cards, of course, is you have to keep the cards busy to get the benefit of it, and that means there's another I/O bottleneck there that needs to be solved. So that's the problem we're solving here. As you can see from the graph here, when we use an accelerator card, the accelerator card gives us, in this case, on the Black-Scholes calculation we were running in this demo, about 8.5 times speed up over a CPU. The nice thing is we're able to take advantage of that speed up from a popular programming language like Python, from a popular framework like Spark, without the end user, without me in this case, having to do any additional work. So the net of what hopefully you could see in that demo is that we showed you how we could use risk analytics, use Xenon, use solid-state storage devices to create these large multi-terabyte data frames, both for ingesting data and for for feeding calculators and storing the results of those calculations for further use, in this case by Apache Spark, in those calculations. So it's simple enough to be run from a Python Jupyter notebook. It's fast enough to be really useful for a quant like myself, and it delivers it all at a lower cost. So that's the fundamental story behind the Levyx Xenon for risk analytics. Thanks very much.